Welcome to TCB. I'm going to talk about selection of electrodes. When it comes to carbon steel to stainless steel, things becomes very complex because one is having very high percentage of chromium and nickel, and carbon steel almost does not have. Very small percentage of nickel and chromium is added, like traces of that are found in carbon steel, for example A106 grade B. So I will take an example. Now just imagine the plate is SS316 or 316L. Now 316 or 304, 316L, these are stainless steel. And here I have got a pipe which is A106 grade B. So 106 grade B pipe is going to be welded to SS316L. That's the condition. That's the case that we are going to talk about. Now, you have to find an electrode that is suitable for both, or a filler that is suitable for both. Now, let's talk about electrode at this point of time. So, how these are done? For this, we use, say, our case is a 106 grade B to SS316. So the selected option I'm going to tell you later, but it is E309 or 309L or ER309L. ER is actually filler rod. We use a diagram called Scheffler diagram. Very interesting. Scheffler diagram is used to determine or to find out what is going to be the right electrode for dissimilar steel or even for stainless steel. Now, Scheffler diagram, in vertical axis, you have got nickel equivalent. Now, nickel equivalent formula, established by Scheffler, which was of course refined over a period of time, is percentage of nickel plus 30 times carbon percentage. So nickel plus 30 times carbon percentage plus 0.5 times manganese percentage. Once you add this, you get nickel equivalent. And on the horizontal axis, you are going to have chromium equivalent. Now, chromium equivalent formula is given chromium plus 1.5 times silicon and plus 0.5 times niobium. So it's chromium plus 1.5 times silicon percentage plus 0.5 times niobium percentage. So once you plot this, these are the lines of phase, different phases. So here below this area is ferrite and martensite. Above this area is martensite. Then austenite. And then austenite is there. Now martensite is also there. So this zone is austenite and martensite. Now this zone is where 0% ferrite. So ferrite percentage increases here. So 5% ferrite, 10% ferrite, 20, 40, 80, 100, and below that it is all ferrite. Now, if you look at this zone, the blue zone and partly green zone here above, this is all austenite. So here ferrite martensite, martensite, austenite and martensite and austenite. And below this line, it is ferrite percentage grows, and below this line, it is all ferrite. So this zone is martensite and ferrite. This is how the diagram shows different phases. Now, if you calculate the nickel equivalent and chromium equivalent of SS316, this will come here. Now SS316, So chromium percentage is 16 to 18%, nickel 10 to 14%, molybdenum 2 to 3%. One of the salient feature of 316 which differentiates this stainless steel from 304 is presence of molybdenum, which increases its corrosion resistance, particularly chloride from chloride. So molybdenum gives more corrosion resistance. So 2 to 3% molybdenum added to stainless steel 304 actually converts it into 316. Now, if the percentage of carbon is lower below certain point, we call it low carbon grade. Right now we are talking about say 316, where carbon percentage is allowed up to 0.08%. If it is L, it will be 0.02% or 0.03%. You don't have to remember. You just look at the chemical composition allowed by the particular grade. But it's so common, it will be low carbon stainless steel grade will have 0.02% or 0.03% carbon. Now sulfur, phosphorus, and all these things are there as per this table, and iron is the remaining is iron. So what makes stainless steel 316 is chromium 16 to 18%, 10 to 14% nickel, and 2 to 3% molybdenum, and manganese up to 2%, silicon up to 0.75%, and remaining will be iron. That's stainless steel 316. Now, if you look at 106 grade B, chromium is only a trace, 0.4% maximum. Nickel, here it is 10 to 14%. It is only 0.4. Molybdenum is 0.15 max. The carbon percentage is 0.3. It's quite high here in A106 grade B, and where it is 0.08% in 316. So, and then look at the other value. So based on that, we can calculate using the formula chromium equivalent is a 0.85. So chromium equivalent of A106 grade B is a 0.85%. And chromium equivalent of SS316 is 19.125. And nickel equivalent will be 17.2% for SS316, which is 9.93% for A106 grade B. Now, if we plot these values, we find carbon still comes here and stainless steel is here anyway. So now, if we have to find electrode suitable to join these two, it will fall in this line. The carbon this electrode or filler to join 316 and carbon steel is going to be in this line somewhere. This much we understood now. Very interesting. Now, one thing is, if a steel does not have any ferrite content in it, that becomes prone for fissure or micro fissure, micro cracks. So 5 to 10% delta ferrite is highly desirable. So if you look at 316 is having 8 to 10% ferrite content, which is highly desirable. So the electrode for SS316 and carbon steel will lie in this line somewhere, but certainly it will have delta ferrite, have higher chromium and nickel equivalent. Now, I have to share a very important concept to you now, which is called dilution. Now, what is dilution? When you are welding two materials, the this face of this base metal will also melt with the electrodes. In the melting, the surface is going to melt So imagine the area C and A both will melt during the welding. Now say this side is A106 grade B equivalent. It's a carbon steel side. So this is carbon steel side. This is stainless steel side. Now, and this is pure electrode deposit. Now at the time of electrode being used at a very high temperature, and you know the flux coating contains alloying elements, and at the time of welding some of the elements will burn out. So for example, manganese will become manganese dioxide, so there will be some burnout loss, and if there's a trace of carbon, this will be picked up, so there will be something pick up, carbon pickup, and certain element will be lost. And what is most important, when the electrode is melting the base metal, higher amount of, say this side is carbon steel. So carbon steel has got high percentage of carbon, for example 0.3. And now electrode which has got much lower percentage of carbon, here when it dilutes, you are going to get enrichment of carbon in the weld deposit here. And stainless steel has got maximum 0.08%. So from the carbon steel side, carbon is coming into the weld pool. And here again, SS316 will not contribute much because it has got low percentage of carbon anyway. So this deposit will have different chemistry than the original that comes from the electrode as well as individual base. So base metal dilution is considered A plus C divided by A plus B plus C. The area that got melted from the base metal both sides will be divided by the total area where electrode deposit was made as well as the base metal melted. So into 100 is percentage. So if you have got even 10% dilution, so which is 5% from here, so imagine 5% of these base metal is contributing a higher percentage of carbon in the weld pool, weld deposit. So our intention, and some chromium also will be lost, some nickel also will be lost, so you need higher nickel percentage and higher chromium percentage, higher manganese percentage to get the right balance, and extremely low carbon percentage to balance these desired condition. So if you look at, now you find an electrode that surfaces which is ER309 or E309L, where chromium percentage is higher than both of them. Now 316 has got 16 to 18%. Here chromium percentage is 23 to 25%. Nickel 10 to 14%. Here nickel is 12 to 14%. Molybdenum 2 to 3%. Here molybdenum is 0.75% to 2%. Here manganese is 29 to 1.06. So here manganese percentage is 1.25. See, carbon percentage is kept extremely low because from the carbon steel side there will be some contribution which will have higher percentage of carbon in the weld final deposit. Therefore, you have to balance with extremely low percentage of carbon in the electrode or the filler. So this gives you chromium equivalent of say 25%. We can also calculate the nickel equivalent. So now if you go back to this, you find 309 electrode or the filler is residing here. And now if you look at this, as I mentioned, this 316 and carbon steel electrode will be found somewhere here. So you will find these 309 has got higher chromium percent equivalent and higher nickel equivalent also. And that's how from this electrode combination, electrode composition, considering dilution, assuming that there'll be some amount of carbon enrichment and some amount of changes in the final deposit chemistry based on the percentage dilution, you select the right electrode. So your right choice is 309. That's how we really get the electrode for dissimilar steel joining carbon steel to stainless steel 316. I hope this discussion was interesting and you understood how electrodes are chosen for carbon steel to carbon steel and carbon steel to stainless steel. One thing is very important. Our intention is to keep the dilution as low as possible, but minimum you should have 5% dilution, because in that case fusion will be better and there'll be sound joint. You don't need 20% dilution. More dilution will cause more carbon enrichment, so it will not be a great idea to have high dilution. So your joint will be prepared, current and voltage will have to be controlled in such a way that not too much of base metal from either side melts and starts contributing to the final deposit. So your intention to keep the dilution should be around 5 to maximum 10% and not more than 10%. And this is how you are going to control the final chemistry at the same time the mechanical properties. So yeah, that's it for now. And if you have got any question, please let me know. Thank you. I hope you understood how electrodes are selected in the first place. Carbon steel to carbon steel to stainless steel, or different grade of stainless steel to another stainless steel grades. Now, once electrode or the filler is chosen, you have to validate the welding. One of the reasons is welding is considered to be a special process. What is a special process? The final property cannot be actually known. For example, once you have done the welding, which is now the joint is completed, you really don't know what is the tensile property, what is the tensile strength. Some of the properties can be checked. For example, you can check hardness. Visually, you can see whether the weld is of acceptable quality. Is there any porosity, crack, or otherwise? But you will not know what is the tensile strength, which is one of the most important property for the welded joint or the yield point. So can you leave it to chance? No. Therefore, you qualify the process, we call it welding procedure specification. So when you select the electrode or the filler, you perform a welding procedure qualification test. In that, what happens? You join two plates, for example, or even you can use two pipes. Plate, both can be used for welding procedure qualification. It is not an essential variable. In other words, you can qualify a procedure using plates or pipes as convenient to you, as per ASME section 9, of course. Now, once you have these, the WPS to be qualified, you prepare the joints and use the electrode within the recommended parameter. For example, voltage, travel speed, and the current, which is given by the electrode manufacturer. And the polarity, of course, and that will also come from the electrode classification. So using those variables, which we call essential variable, where you cannot change those parameters which will impact the quality of final deposit or the properties, are called essential variables. So within those variables, keeping those variables in mind, you are preparing the welded joint. Once the joint is prepared, then you will cut samples from them. So for the pipes, there are locations specified from where you have to select the sample for plate welding. when plates are used for procedure qualification, if pipes are used for qualification, where you select the sample from pipes. So I will show you now. Once you have selected the electrodes, then you prepare a proposed WPS where you decide what is the type of joint going to be. It's a single V or double V, single bevel, thickness, and all those based on the proposed parameters. You prepare a joint, you perform a welding, look at the weld quality is acceptable, because you have to make sure at the time of testing mechanical properties, there is no welding defect that can be the causal factor for the failure of the joint, because otherwise you feel the material combination is not acceptable. So you have to make sure from the sample which will be tested for procedure qualification, there is no defect. You make sure there's an X-ray or test done to make sure that the joint not have any problem, and then it is tested, and the testing is performed to make sure the minimum requirement for the electrode specification as well as the plate meets the requirement. Once this is done, it's a validated process, we call it. Then you keep all those records, we call it procedure qualification records. So procedure qualification records, which is basically the test records, will support the proposed WPS. So the WPS becomes a validated procedure. And the welder who did the welding for the procedure qualification also gets qualified as a welder once the WPS is qualified. Because if he has not done the right joint, how the joint itself would have been qualified. So procedure qualification test can qualify the welder who did the procedure qualification welding. I will show you now how the samples are taken from pipes and plates. Give me a few seconds. I'm going to show you where you take a sample for tensile test and root band and phase band when it is a plate sample welded for the test. So here it is. First, you are going to discard the ends because there may be some defects at the start and stop point. So you remove some part, discard this, and then you make a reduced section tensile test sample from here, and then root band, phase band, root band, phase band, and then another reduced section tensile test, and then discard the ends again. So if this was the weld joint prepared, a single V, and this joint was welded, from there, this plate you make two reduced section tensile test, two root band and two phase band samples. For the thicker plates, you can take side bands and side bands from here instead of root or phase band, and reduced section tensile test can come in between. So this is how the samples will be tested, and once they meet the requirement of the plate, the procedure is qualified. So the electrode that you have selected is also validated to be the right electrode. I hope this discussion, including selection of electrodes for similar material, for dissimilar material, as well as validating them by welding procedure qualification, is clear to you. One thing is, those records of the test, once you keep, these are called procedure qualification records. So procedure qualification record would include tensile test sample, bend test samples, Charpy test samples, hardness, and all that. And one thing is important, the welder who did the welding for procedure qualification also gets qualified, because if he or she was not qualified, how he or she has produced the joint which got qualified. So the first welder can get qualified based on the procedure qualification itself. Subsequent qualification of the welders are done based on the approved procedure. That's the rule for welders qualification.